Welcome, Windows developers and AI experts. I wanted to start today's session with a survey, but since I can't see you raise your hands, click the like button if you've ever opened a cloud invoice and felt your stomach drop. You might have experienced this when adding cloud-backed AI models to your app. Your users end up loving the feature and use it constantly, which is awesome, but then you get the bill for all that cloud resource usage. What if we could change that story? What if we could run the same model locally using the hardware the user already has and still build the same amazing features that users love without the bill at the end of the day? Using AI locally means that instead of a bill, you get better privacy, lower latency, offline support, and finally those cost savings we mentioned. Many top ISVs are already using local AI on Windows to delight and empower their users. Today, we're going to show you how you can run your own custom or open source AI models locally on Windows using Windows ML. I'm Andrew Leader, a product manager on the Windows ML team.
And I'm Maha Bayana, and I'm a software engineer on the Windows ML team.
So Maha, what models can you use with Windows ML?
So Windows ML works with ONNX models, meaning you can choose from over 40,000 ONNX models from Hugging Face. Or you could choose from 229,000 PyTorch models and use the WinML CLI or PyTorch to convert them to ONNX. You can also train your own models to achieve exactly what you need and convert it to ONNX format. So once you have an ONNX model, you can run it on Windows ML, but if you want to run it on the best possible across GPU and NPU, you can even optimize your model for each IHV. So you can use the WinML CLI to optimize your models, and then the WinML allows your app to accelerate your models against a wide variety of Windows hardware without shipping specific SDKs or each hardware variant.
That sounds really great. Some of my users are still on Windows 10 though. Can I still use Windows ML?
Yeah, of course. So Windows ML is built for varying needs on Windows developers supporting operating systems back to Windows 10.
That's excellent. A few of our apps are written in C though. Can I use Windows ML with C?
Yeah, of course. You can use Windows ML directly with C apps, you can even use Python with Windows ML, or you can use C# and C++ too.
That's perfect. I've got a number of old apps that could really use local AI, but the way I package and deploy them is a little bit outdated. Can I still use Windows ML regardless of how I deploy my app?
Yeah, of course. So Windows ML supports both unpackaged and packaged apps and also supports self-contained and framework-dependent deployment techniques. So you can truly build your app however you want while leveraging Windows ML.
That's amazing. I'm sold. All right, let's build something. So in today's session, Maha is going to be building a customer support sentiment analysis dashboard that takes our incoming customer support messages and uses a sentiment analysis model to classify each message's sentiment into positive, neutral, and negative buckets so that we can see the overall trends of our customer feedback and notice when a negative event is occurring and react to it quickly. By the end of this session, you'll learn how to use Windows ML to convert and optimize a model from Hugging Face to run on NPU, GPU, and CPU Windows PCs, and then use that model in a website running inside Edge or Chrome, and then finally use that same model in a native Windows app for even better Windows integration. All right, let's get started. Maha, can you show us how to use the Windows ML CLI to convert and optimize a model to run on Windows?
Yeah, so for those of you who aren't familiar with Windows ML CLI, it's a new command line tool with a variety of model conversion and optimization tasks. So this CLI supports a number of commands. So let's get over here and let's start by running our WinML hub command. Now this command helps to see what a bunch of models it supports, and let's go ahead and run this, and it's going to take a second over there. All right, so it looks like there's a sentiment analysis model over here, and that we could use for our tasks. So let's go ahead and export that into our project using this export command over here. So let's go ahead and have that export command, and we're going to run that, and that's going to take a second.
Awesome. And while that's exporting, can you tell me how you know what all those models are for?
Yeah, so all of these models are from Hugging Face, like the one right here, like the sentiment Twitter analysis model that we are using. So you can find the models on there, read their descriptions, or you could even ask Copilot about them.
Oh, that's great. Yeah, I think I could make sense of that. And this ONNX model, will it work on all Windows PCs?
Correct. So this model will work on CPU devices to reach across all Windows PCs, but can also be accelerated using like NPUs and GPUs and so on.
Awesome. So now that we have an ONNX model, can we use this in our web app?
Yeah, so let's open up our web app over here so we can look at some of the code here. So this is our customer support dashboard, and the goal of this app, as you said earlier, is to classify these incoming customer support comments and reviews into 3 different categories: positive, negative, and neutral.
Got it. And which web libraries will we be using in this app?
Okay, so we're going to be using ONNX Runtime Web, which essentially lets us use ONNX models and works with WebNN behind the scenes to run the sentiment model that we exported earlier using that 𝗦𝗽𝗲𝗀𝗇𝗏. So let's go ahead and see how we can get access to the ONNX Runtime Web. So we've already run npm install ONNX Runtime Web in this particular project, and then we're going to go up here to this code at the very top, and we're going to use this one line over here, which is import ORT from ONNX Runtime Web, and this is still an experimental feature, thus you see the /experimental as a part of it. So for WebNN, I also enable some developer preview flags to enable WebNN, since right now it's currently in developer preview mode. So we can go ahead to the browser over here, and as you can see in these flags, we have these particular WebNN API flags and WebNN flags set over here in order to use WebNN.
That's awesome. Now that we have our prerequisites, how do we use our model in our web app?
Yeah, so let's look at some code here again. Yeah, so first we fetch our model in this section of the code. So as you can see over here, we're basically using the model base path, and we're getting that model that we initially exported using 𝗦𝗽𝗲𝗀𝗇𝗏.
So that downloads the model onto the user's device, but then after that it runs locally?
Correct. So other than the CDN cost of the initial model download to the user's device, which we can cache for future reloads, everything else runs 100% locally on the user's device.
That's awesome. I love the sound of that. So how do we load the model?
All right, so to load the model, we need to create an inference session. And in order to create an inference session, we're going to start by creating context. So first, we're going to look at the API over here, where we're going to basically use the create context API in order to tell the device what kind of hardware we want to use. So in this case, we're going to use the CPU. So we're going to set our device type to CPU. For step number 2, we're going to go ahead and create our inference session. Now, in order to create our inference session, we're going to use this API right over here, which is ort.inferencession.create. Now, once we have that API in place, we want to give it a couple of metrics to specify what kind of hardware and what kind of EPs we want to use. So we're going to go ahead and set our EPs to be WebNN, our context, which we set in the earlier step, and then we're also going to set those model ONNX data that we got from our 𝗦𝗽𝗲𝗀𝗀𝗀𝗀 CLI from earlier.
Excellent. Is there anything else we need to do before we run this?
Yeah, and for the rest of the code, essentially, we're just validating input, tokenizing and tensorizing the input, and then basically just running it in the session that we created. It also runs softmax on the logits after inference, and that's essentially just to map these probabilities into their own sentiment categories.
Got it. Sounds great. Can we run the app and see it work?
Sure, let's do that. So let's go ahead and run our app. So we're going to simply do that by typing the command python server.py. And once we do that, we can go ahead and open our local host web app over here. And yeah, as you can see, it's going to take a couple seconds to load that model and get that EP set up. But once that happens, we can see the model up and alive. As you can see that we have all of these messages on the right side of the screen, and these are basically incoming messages that are being classified into positive, negative, and neutral. And then to the left of the screen, you can see that we have a little sentiment analysis chart, and this is essentially taking each one of those sentiments, converting them into a chart so you can kind of see that sentiment over time.
That's really excellent. And so this is all running on the CPU though, right?
Correct. So how about we make this a little bit faster?
Yeah, that'd be great. I heard about these devices that have NPUs. Can we leverage the newest NPUs with WebNN?
Of course. So let's go ahead back a couple steps. And remember how we set that create context part? So we're going to go over there and we're going to change our required device type from CPU to NPU. So once we do that, we're going to go ahead and save the file. And then we're going to go to our browser and reload our site. So again, that's going to take a couple seconds to load our model and our EP, but we should see it in just about a moment.
Wow, that was a really simple change. And it's running so much faster now. This is really awesome.
I know, right? It's so much faster. As you can clearly see, it's classifying those incoming messages much faster into their sentiment categories. And we also have this chart that's like updating in real time much faster than what it was doing with the NPU.
Yeah, and the rest of the device stays responsive since it's all processing on the NPU. This is really perfect, but it gives me an idea. What if we could have a floating overlay so that this chart is always visible on the top right of the user's screen, and then our support manager can keep an eye on things while working on other tasks? Could we do that?
Yes, that sounds awesome. So let's go ahead and use our native WinUI 3 app. So let's convert this web app into a native WinUI 3 app in order to get that floating overlay.
Yeah, and we can use the same ONNX model with that Windows app?
Correct. So you can use the same ONNX model that we downloaded using the WinML CLI, pretty much just export it the same way we did before. All right, so in this WinUI 3 native project, I've installed the WinApp SDK ML and WinApp SDK runtime packages, which adds WinML and ONNX Runtime to our app. So as you can see in the packages part of this file, you can clearly see that we have these packages installed over here.
Yeah, and that runtime package, that adds the Windows App SDK framework-dependent version, so our app can be smaller and not carry as many binaries?
Correct. It saves about 40 MB of binaries that we'd otherwise have to carry in our app.
Nice. Okay, so once we have those installed, what's next?
So next we have our app install and register the WinML execution providers.
Okay, I've heard about execution providers. I think those are SDKs built by the hardware vendors like AMD, Intel, NVIDIA, and Qualcomm, and they allow us to accelerate our models on their NPUs, GPUs, and CPUs, right?
Correct. So WinML allows us to dynamically acquire these providers, meaning that our app doesn't need to carry 80 MB of providers, further reducing our app size and simplifying our distribution.
Awesome.
So we can use a few steps in our code to acquire these EPs. So let's go ahead and scroll down to this part over here. So first we're going to create our ORT environment using this particular line over here, which essentially just creates an ORT environment instance. So once we've done that, for step number 2, we're going to have to discover the compatible EPs with our execution provider catalog. So we're going to jump down to this particular method over here, and you can see that we're going to be using the find all providers API in the list to essentially list all of the execution providers that are available to us. Now, for today's session, we're going to be using the QNN EP. So we're going to sieve through all of these execution provider lists that we have in a for loop and look for our specific EP, which is the QNN one. So once we have our QNN EP, for step number 3, we're going to go ahead and call ensure ready async API on our particular EP. Now, this is essentially going to help make that EP ready. And once that EP is ready, we're going to go to step number 4, which is essentially registering that EP to our environment. So we're going to go ahead and use this API down here, which is try register in order to register our EP to ONNX Runtime.
Got it. And so if the EPs aren't on the device, those actually get pulled down through Windows Update, is that correct?
Correct.
All right, now that we have those EPs on the device, how do we inference against a specific EP?
Yeah, so to run a model inference using a specific EP, we need to use something called as session options. Now, we can set quite a few metrics in the session options, so let's go ahead and scroll down to this part, which essentially sets those metrics. So over here, we can see that for step number 1, we're kind of using that API called getEPDevices in order for it to give us all our EP and device combinations. So the one that we're going to be using for today's session is going to be our QNN EP with the NPU device. So we're going to sieve through all of those combinations over here in order to look for that specific one. So for step number 3, we're going to go ahead and use our append execution providers API, and we're essentially going to get that QNN NPU that we found from earlier, and we're going to append it to this particular session options, so we can tell our inference session, this is what we want you to run on. And then we can also set a couple of other options with our session options. For example, if I don't want my session to run on the CPU and I completely want to disable it, I can use this add session config entry API. And in this API, as you can see over here, we're essentially just saying disable the CPU fallback. And yeah, you can also use some other APIs like set execution policy, or set EP policy, and that will essentially help you prefer one sort of hardware over the other. So in this case, that would be our NPU over the CPU.
Excellent. Yeah, that code looks pretty similar to our web code. It's pretty neat how we can use the ONNX runtime on both web and native and share a lot of the code.
Yeah.
And so did you already implement that pop-out feature we mentioned?
Yes, so we can go ahead and click on this button right over here, which is pop-out overlay, and you can see that that kind of pops out a little sentiment chart to the right top of your screen. Now, the nice thing about this is you can always have it at the corner of your eye. So let's say you're talking to Copilot or writing up some docs, reading your emails. It's always at the corner of your eye, and you can kind of keep track of that sentiment over time. So we can go ahead and click our Word doc over here, and it's still the corner of your eye.
That's perfect. And it's still running so fast because it's all using the NPU and the device still stays performant and the CPU isn't getting bogged down.
Correct. So we can look at the task manager over here, and you can clearly see over here that it runs on the NPU.
That's amazing. Great work, Maha. That looks excellent.
Yeah, thank you. I can't take all the credit for it, though. Windows ML has definitely made it much, much easier to use local AI on this device.
Yeah. Speaking of what's new with Windows ML in 2026, we started today with the Windows ML CLI tool, which is a new tool that helps you convert and optimize models to run locally on Windows across CPUs, GPUs, and NPUs. The Windows ML ORT GenAI library has also received a number of performance updates, leading to faster local LLM inferencing on Windows. And Windows ML itself has been updated to version 2.0, bringing the ONNX Runtime 1.24, which includes a number of performance and stability updates, and some newly updated plugin-based execution providers that have performance updates and allow you to use the execution providers across different runtime versions more easily. And finally, WebNN is being updated to use Windows ML when on Windows, as we saw earlier, leading to faster hardware-accelerated machine learning model inferencing when on Edge or Chrome browsers. And if you're looking to try Windows ML for yourself, you can install the AI Dev Gallery app. It includes numerous samples of various AI models running locally via Windows ML, and it includes code samples so you can easily use those models in your own apps. And finally, I wanted to highlight some other local AI solutions on Windows. Windows ML is part of the Microsoft Foundry on Windows, which provides 3 main local AI solutions. If you're not a machine learning expert like Maha, you should check out the Windows AI APIs and Foundry Local, both of which provide ready-to-use AI models that require no machine learning expertise. These models are pre-optimized and installed system-wide, allowing you to focus on writing your code rather than optimizing models. But if you need something custom that you can't find in AI APIs or Foundry Local, you can use Windows ML to run any custom or open source model. To learn more about Windows ML, you can visit aka.ms/windowsml to see our documentation. Additionally, we'd love to hear your feedback. Please email us. And finally, check out our other sessions at Build 2026, including Breakout 260, which covers everything in Microsoft Foundry on Windows. Thank you all for watching. We can't wait to see what you build using Windows ML.
Thank you.